Hey, Algebra 1, we are going to be solving quadratic equations by graphing. Now, I'll be honest with you, I do not find this the most elegant way to solve things, but this is a good practice for us to remember what a quadratic equation is. See, remember what a quadratic equation is and how we solve it. So we have in the past solved quadratic equations by factoring. That was our one trick pony that we have. We can solve it by factoring. And this is a great method as long as it's factorable. If it's not factorable, then we run into some problems. So you remember the deal. What we would do is we would take this particular quadratic equation, make sure we set it equal to 0. We'd factor this side and make sure we remember that since both factors were equal to 0, the product of both factors is equal to 0. We know that one of the factors has to equal 0, and then from there we get x is equal to this, and or I suppose x is equal to that, and we get our two answers, and hooray, we're good, right? You remember that? Okay, so what our textbook has us doing is considering graphing as a way to solve such situations, particularly when we can't factor. So we're going to practice that concept. So the first term that we need to be aware of is the idea of what a quadratic equation is. So a quadratic equation is an equation that can be written like this: ax squared plus bx plus c equals 0. Please don't confuse it with what we're going to talk about as well in this section, the quadratic function. And so I'm going to try to be distinct about calling this a quadratic function as it's a relationship between y and x. Here, this is some equation. I want to solve for x. X has a finite number of solutions. I can solve for x. There is an x, okay? So that's our quadratic equation. The next thing we want to talk about is our roots. Roots of an equation refers to that which will make this 0. So the x values that satisfy this equation, x values that work here. Okay, so the x values that work here to bring off a 0 answer are called the roots of the equation. And similarly, we can talk about the zeros of an equation. The zeros of an equation really refer to, if I were to graph this related function, this y equals ax squared plus bx plus c, I would graph it and I'd get some parabola that might look like this. The zeros of the function are the values where the graph crosses the x-axis, where those values are 0. And you might realize that zeros and roots are very similar, as they often refer to the same thing. So that brings us to example 1. Here in example 1, we're going to have a situation where we have two roots. And so how do we get these roots? So what we have to do first of all, in order to solve this by graphing, is to graph the related quadratic function. So y will replace 0, and we'll have x squared plus 6x minus 7. So this is what we're graphing. And if you don't like the way this is, which a lot of students don't really like that, we can just move things about so that instead of saying that function is equal, or x squared plus 6x is equal, minus 7 is equal to y, we can do it this way. Okay, same thing. Basically, all we did was replace the y, let the y substitute and replace in the 0. Okay, so now we're going to graph this. You remember from the last section how we graph these quadratic functions rather simply. What we do is we will make a table. We only are going to have 3 different entries. Let's do that. And the first entry we're going to get by figuring out what the axis of symmetry is. We know the axis of symmetry is negative b over 2a. And so when I calculate that, that gives me some good information about my parabola. That's going to be negative 6 over 2 times 1, which is x equals negative 3. This also gives me the x coordinate of the vertex. So let's put negative 3 here. I'm going to highlight this little box red because this little box will be referring to my vertex. Okay, so the vertex is here. So how can I figure out the y value? You know it. Plug negative 3 right into the original equation. When I do that, I get that negative 3 squared is a positive 9 plus 6 times negative 3, negative 18. and then minus 7. So this ultimately becomes negative 9 plus a negative 7, which is a negative 16. So this is my vertex. We know that it is a happy parabola, so we also know that this is the lowest point. So all of our values are going to be above. Let's go ahead and try some values on one side of the x. So we know that we've got our axis of symmetry of negative 3. We know we're going all the way down to negative 16. Let's find values like, let's say, negative 1 and positive 1. If I plug negative 1 into this equation to find the corresponding y value, I realize that 1 plus a negative 6, that's going to give me a negative 5, plus a negative 7 is a negative 12. I did that just by substituting. I'm going to do the same thing with a positive 1. When I put a 1 in here, 1 squared is 1. Plus 6, that's 7. 7 minus 7 is 0. And the reason why I only chose to do 3 points is because I know what's happening on one side will happen on the other side because of symmetry. Remember, our vertex is located on the axis of symmetry. So I went 2 spaces to the right. Let's go 2 spaces to the left. So at negative 5, we expect negative 12 to be happening, right? And if we go 4 spaces to the left, we're going to be at negative 7. So at negative 7, we expect to be at 0. So this is some good information to help us graph. And so we'll get started with our graphing now. What we did here is we basically just came up with a XY axis or a coordinate system such that we knew we could fit the values that we got here on to our graph. And so what I have here is that x is equal to negative 3. I'm going to put that in gray. That is just our axis of symmetry. And now I'm going to plot some of these points down. And so when I do so, let's go ahead and use that color. I know negative 3, negative 16, that's my vertex. Negative 1, 12, negative 12, that's going to be this point here. And let's go ahead and exploit symmetry. At negative 5, I'll also be at negative 12. So let's go to positive 1, 0, that's here. And at negative 7, we're at 0 as well. And you can see how beautiful that looks. And so here, we've done the job. We've drawn the graph. The graph is gorgeous. We're feeling good. But how does this solve the equation? So how does this solve the equation? We graphed the related function, quadratic function. We graphed it. We did all the things that we learned in the last section. And then what we need to look for is when y is equal to 0. When is y equal to 0? It's equal to 0 at the x-axis. It's equal to on the x-axis. On the x-axis. And so what we see is that these two are the values that are the roots. So we have a 0 at negative 7 and we have a 0 at 1 because the y values were 0 at both of those points. So that is those are the solutions. So x is equal to negative 7 or 1. Actually, I think we could have factored this when I look at these answers. Let's see if we can do the next example. In this example, we're going to get something called a double root. And I'll scooch back up to the last example. Here we got 2 different roots, 2 different values. A double root means that we're going to get the same value twice. And let's see what that looks like. First of all, you see that we have this quadratic equation that is not in terms of x, so it seems a little bit weird. But there's nothing wrong with changing the variable and then working it that way if it makes you happy. If it doesn't, that's okay too. But since we're going to graph it on the xy plane, I think it just kind of makes sense. X squared plus 4x plus 4 is equal to 0. By the way, I always like to, if I can, make sure that my lead coefficient is positive if I am solving for, if I'm setting everything equal to 0. It's just what I do. But, it's up to you. And now what we're going to do is actually put a y here. So we're going to rewrite this such that we're saying y is equal to x squared plus 4x plus 4 instead of saying 0 is equal to that. And so now we're going to graph this, and we remember all the procedure. First thing we need to do is find the axis of symmetry. X is equal to negative b over 2a is how we're going to find that. So the axis of symmetry is negative 2. After finding the axis of symmetry, we want to find the vertex. Recalling that the vertex is an xy point, we're going to have to find both x and y. We're going to do that by plugging in -2 for the x and figuring out what y is. When we do that, we get that 0 would be the corresponding y value when x is equal to -2. Okay, so that's our vertex. So now we're going to make an x and y table such that we're only going to use 3 values because that's all we really need. So we have -2, 0. Let's choose some points on the right side. So we're going to do -1, figure out what that is, and then figure out what the value is when we plug in 0. And so we're literally just plugging it right into this equation here. And when we do that, we get these values here, and those values also, let me highlight my vertex, those values also speak to what's going on the other side of this point -2, 0. So at -3, we're at +1, just exploiting symmetry here, and then at -4, we're at a +4, again exploiting symmetry, looking at what's going on either side. So now the graphing should be pretty easy for us. We should be able to handle it pretty well. Let me set up my coordinate axes so we can get started. So then we get this shape, right? We get these nice 5 points that give us an excellent guideline as to what our graph looks like. So nice trip down memory lane in terms of graphing a parabolic function or a quadratic function. However, what we need to make sure we remember is that when we're solving these problems, we're using this only as a tool to figure out what are the values that are going to make this equation 0, thus figuring out the roots. And the value singular that makes this 0 would be -2, and we saw that here when we found the vertex. So this is considered a double root, because when we solve quadratic equations, it's not unlikely for us to get 2 answers. In fact, we always get 2 answers, except when we have a double root like this. All right, so let's go ahead and see if we could put some more information in our minds with the next example. All right, so let's get started with example 3. So in this example, we're going to have a situation where there is no real root. Now, we know that we're solving by graphing, so we're going to start off by replacing y, making 0 with y, and then graphing that. Couple things that we know we need to do. First, we're going to find the axis of symmetry. And to do that, we know that x is equal to -b/2a. In this case, that means that x is equal to the opposite of 1, which is a +1, over 2a, which is 2. So the x coordinate of the vertex is going to be 1/2. If the x coordinate of the vertex is 1/2, we need to find the y coordinate by plugging 1/2 into the equation. 1 squared is going to give us 1/2 squared is going to give us 1/4, minus 1/2 plus 4. This will become -1/4. When I add that to 4, I get 3 and 3/4. Hopefully that made sense. So that's going to be our vertex. If I were to substitute 1/2 in, that's what my y value would be. Okay, and so now I'm going to choose 2 points on the left side of the equation of the vertex rather, and so I'm going to go up a half like that, 1, and then I'm going to go up a full step again, and I'm going to go to 2. So notice if I go up a half step here, I need to go back a half step when I'm exploiting symmetry. So going back a half step is going to get me at 0, and then going back a full step will get me at -1. I hope that made sense because we want to be symmetrical. So let me actually put in our axis of symmetry. Our axis of symmetry is here at +1/2. So let's go ahead and draw that in as neatly as I possibly can. Let's see if that's working out. Sort of, kind of. You guys get it. So that's our axis of symmetry. Our vertex is located at point 3 3/4. So let's see, here's 3 3/4 would be around right here. So that's the point that we're talking about. That's the point that we've highlighted in red. And so now we're going to do the other part. I don't know why that's not coming up. We're going to do the other part, which is to graph the other values, or at least calculate the other values. So if I put a 0 in, let's say, into this equation, I know that the resultant value is 4. Since this is 1/2 space to the left and this is 1/2 space to the right, I know this value is 4 too. Again, exploiting symmetry, right? So here and here, we're going to have the same values. And now from there, I'm going to take one full step. So if I were to calculate, let's say, -1 and plug it into this equation here, -1 squared is going to give me 1 minus a -1 will actually give me a +1 plus 4. That's going to give me a 6. And so if that value is 6, when I plug 2 into the equation, which is equal in distance from 1/2 as -1 is, I'm going to get a 6 here. All right, you guys are with me? I hope so, I hope so. So I'm going to plot that information. I know I've got 1 point here, 1 point here. And then when I step out, I'm up at 6, which is around here and right here. And again, I get these beautiful graphs of these parabolas. And remember, we're just really reviewing. That didn't go well. We're just really reviewing graphing, but we're also using that review of our graphing to talk about how that affects the equation here. So what I see is that this graph never crosses the x-axis. Because it never crosses the x-axis, I know that there is no solution because there's no real value that I'm going to plug into this equation to get it to equal 0. So this situation has no real solution. So here in this example, it's titled rational roots, and sometimes our roots won't be double roots that are nice and perfect, or nice two different roots, or even the idea of not having any roots at all. Sometimes we'll get roots that are kind of hard to distinguish, and they're called rational roots. They are real numbers, but they just aren't necessarily easy for us to tell where they land. So here it says we're going to solve this by graphing, and if the integral roots, that means roots that are integers, the ones that we like, if integral roots cannot be found, we're going to estimate the roots by stating the consecutive integers between which the roots lie. So let's go ahead and get all the information down that we know we need to when we do one of these problems. Okay, so I took the liberty to do as much as possible. We found the axis of symmetry to be -3, put -3 there, figure out that the vertex was -3, -2, build off the vertex by using symmetry to choose points on either side of -3 in order to calculate a number of points, 5, which we like, and that seems to work out well for us. So let's go ahead and do what we're doing here. So if at -3 we're at -2, that means there's 1 point here, that's our vertex. And then if at -2 we're at -1, then that means that's also happening at -4. And then also if at -1 we're at +2, then we'll have a similar thing happening at -5. And so here's what you see. You see that our parabola does not cross the x-axis at an integer value. What we see, let's see if that side's always hard. What we see is that our parabola will cross somewhere between these integer values. So between -1 and -2, and also between -4 and -5. That's where we'll have the values that we are looking for, the roots as it were. We could write our final answer as root 1 being between -2 and -1, and root 2 being between -5 and -4. Our final example, example 5, is going to talk about estimating solutions to a problem. So when a football player punts a football, he hopes for a long hang time. Hang time is the total amount of time the ball stays in the air. A time longer than 4.5 seconds is considered good. If a punter kicks the ball with an upward velocity of 80 feet per second and his foot meets the ball 2 feet off the ground, the function here represents the height of the ball, y, in the feet after t seconds. So t is going to represent time. What is the hang time of the ball? So this problem is going to allow us to take some time and use a graphing calculator to actually do it, which is great because I liked introducing you guys to some concepts. But let's think about what's going on. We have an unhappy parabola. We know that when at 0, we can plug a 0 in here. We know that the parabola starts at +2 And you think about it, it's going to go up and come down, right? Because that's what balls do when they are kicked. They're going to go up and come down. So that's the height of the ball changing. And we've got this thing here. And we know that X refers to the time. So this part down here, really we want to know how long, what the time is that this whole ball takes to go up and come down, and that'll give us the hang time. So what we're going to do is use Desmos, which is a really nice app, to figure that out. So I'm going to come back here and grab my computer browser and go to Desmos. Literally type in DESMOS and you'll get this really cool calculator that would cost money if we had to buy it. Like, it would be really expensive because it's better than like a calculator that we can get on the market. Okay, so let's go ahead and put the equation in there. So we had y was equal to negative 16 t squared. I'm going to use x squared because I think the calculator will be happier if I did that. So negative 16 x squared plus 80x. I think that was the initial velocity, and then it was plus 2. And so this is our graph. This is kind of hard to see, so I like to come over here where you see the little wrench here. We can change the graph settings. I don't really need values that are like negative 10 for my x-axis. I'm going to go to negative 1 just so I can see the axis where it crosses and things like that. And then I'm going to probably just go up to, I see the graph comes down here at 5. Let me go to like 7 or something. So that gives me a wider perspective. And now I need to consider the y-axis and how high this ball can go. So I'm going to first change it to, let's say, like negative 1, just so I can see the y-axis there, and or the x-axis rather. And then I'm going to go to, let's say 100. Let's see, does it get 100? Oh, that seems pretty good. That was pretty good. Let me go to 120 so I can get the entire, that was 1,120. Let's try that again. 120 looks perfect. Okay, so now I'm going to kind of grip my graph over here so you guys can see a little bit better what's happening. So this is really nice. So you can see that it doesn't start at 0, it starts at 2, the ball goes up, comes back down, and you could see how long it took. So looking at the graph, you can see that by about a little bit after 5 seconds, it hits the ground. So what you can see is that the air time is approximately 5 seconds, just from looking at the graph and using a tool like Desmos or a graphing calculator. Okay, so we will be using graphing calculators in the future. If you haven't played with Desmos before, please do so, because it is pretty cool. All right, so from that information we can put approximately 5 seconds for the t time that we would get here, which would give us the total time. All right, guys, I hope that made sense. I look forward to talking to you guys soon. Let me know if there's some questions or concerns, and we'll talk about them. Take care.